Hi, everyone. Welcome to lecture 23. In this lecture, we'll start talking about studying the atmospheres of exoplanets. And then in the second part, we'll talk about how the studies of exoplanet atmospheres will potentially help us understand if there are life on any of these planets or not. But in this section, I'm mostly going to talk about the process of studying exoplanet atmospheres. So the basic way that we can learn about atmospheres of exoplanets is the same way that we learn about the composition of stars like the sun. Basically, you take a spectrum, you take the light from that star, or in this case, that planet, you split up that light into different colors, and you look for the fingerprints of different elements to try to figure out what this object is made out of. So this is basically the same process as what astronomers did for the sun about a century ago. Here's what the spectrum of the sun looks like. The light from the sun split up in different wavelengths. You can see that there's both this overall shape to the spectrum of the sun. It's this black body, which tells us that the sun is a dense ball of gas that is made of very hot material. The temperature is something like 6,000, 5,700 Kelvin. And it also has these little spectral lines that indicate that there are elements present in the surface of the sun. And if you take a spectrum with very high detail and you look for all of these little black bands and try to correspond which molecules they are, or which atoms they come from, and figure out based on your calculations how much of that atom must have been there, you can infer that the sun is mostly made up of hydrogen using a spectrum like this. This is the process that Cecilia Payne-Gaposchkin did early in her career and was able to figure out that stars are mostly made up of hydrogen and helium, unlike what people thought at the time, which is that stars were made up of similar elements to that of the Earth. So how can we do this for exoplanets? If you wanted to do that exact same process, basically what you would do is you would take your telescope, you would try to point it towards a star with an exoplanet near it, and you would try to get light from the exoplanet only. Now, this means we need to directly take a picture of an exoplanet. And as I told you in the last lecture, that's very hard. It's almost as hard, it's the same order of magnitude hard as trying to figure out if there's a firefly next to a lighthouse from across a continent. It's very, very difficult. So what do we do instead? Another problem is that Earth's atmosphere is blurring things out consistently. So over the last couple of decades, our technology has improved to the point where we may actually be able to start making progress on taking images of planets, and we actually have been able to do that for some planets. And the key advancement in technology is called adaptive optics. So what happens when you are observing a star through the atmosphere of the Earth is that the Earth's atmosphere bends the light ever so slightly. With adaptive optics, you can essentially unbend that light back at your telescope. You can shine a laser up through the atmosphere, use that to measure how the atmosphere is moving, and then send signals to what's called a deformable mirror, which can essentially correct for the deformation of the atmosphere by undoing that in the mirror. And when you turn on your adaptive optics system, you can go from an image that is very spread out and scattered, like this image of the star here, these little speckles that you can see. And when you turn on the AO system, you get this nice, smooth, sharp image, this dot there. So adaptive optics allows us to compensate for Earth's atmosphere and take much sharper images than we could have otherwise. So using this technology, we can actually now image superjupiters around other stars. These are real images of planets around another star. This is the star HR 8799. This big black region here is where the star is. What they have done is they've put something called a coronagraph over it. It's essentially a very high-tech version of your thumb. If you put your thumb up to the sky to block out light from the sun so you can look at something nearby, but it's inside of the telescope. And you can see on images taken over many years that there are these four dots that are moving all around the star. There's one here, 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 and here. These are the planets HR 8799 B, C, D, and E. And these are perhaps some of the nicest images of planetary systems that we have today. So because we can make these nice images of superjupiters and we can separate the light of these superjupiters from their stars, I call them superjupiters because they're about 10 times the mass of Jupiter, but we still think that we would consider them planets. Because we can actually take these images, we can take those images and we can split up the light into different colors. So let's take this innermost planet here, which is called HR 8799e. And let's look at what we get if we take the data, we take the light and we split it up into different colors. You can see here that there's this little dip in the data. So the data here are orange and purple. The orange is taken with a telescope called the Very Large Telescope in Chile. And the purple are taken with the telescope called the Gemini South Observatory, which is also in Chile. And you can see that there are these little wiggles, and these wiggles correspond to places where water has absorption lines. So from this, we can infer that there is water in the atmosphere of this planet. So these are super Jupiters. Can we do anything about the smaller planets? We can't image those yet. We need much better technology. Our technology is still very immature when it comes to taking images of most of the planets around other stars that we can see. But perhaps there's another way that we can do this. So recall that most of the small planets that we know about have been found with transits, and in particular, using the Kepler Space Telescope. Kepler measures the transits, these dips in brightness of the star as planets go in front. And recall also that transits reveal the size of a planet. The bigger the planet, the more light it blocks. But what about planets that aren't the same size at all wavelengths? So imagine the following. This is a real image of the Earth. You can see here the edge of the Earth, which we call the limb, is this fuzzy area. And that's because Earth has an atmosphere. And you can see that the atmosphere is essentially fading away into nothing as you go close to the edge of the Earth. The Earth does not appear to be the same size in all colors of light. So what I'm going to do now is I'm going to go from this kind of visible light true color image to what the Earth looks like at a wavelength of 8.6 microns. This is an infrared image of the Earth. And what you can see is that at this particular wavelength, the atmosphere is essentially transparent. You can't see any atmosphere here at all. It's this sharp edge where the edge of the Earth ends, where the solid edge of the Earth ends. But at a very slightly different wavelength, 9.6 microns, now we're at a wavelength where part of the atmosphere is opaque. That's because there's ozone in our atmosphere, and this ozone gas blocks the light and makes the Earth appear slightly bigger. If I go back and forth, you can see that at 8.6 microns, Earth appears slightly smaller than it does at 9.6. And that's just because the ozone is opaque at 9.6 microns and it's transparent at 8.6. And therefore, we can see this slight change in the size of Earth. If we can see a change in the size of Earth just by eye, then perhaps we can see it in transit observations as well. Because if you imagine that the Earth looks very slightly bigger at this wavelength when we observe it with transits, it should make a very slightly deeper transit at this wavelength. This is the idea behind transmission spectroscopy. Basically, we're trying to measure the transit depth in all different colors of light. And we look for wavelengths where the transit is very slightly deeper, and therefore the planet appears very slightly larger. If we see the planet is a little bit larger, then we can infer that there is a molecule in its atmosphere that's blocking light and causing it to look a little bit bigger to us. If you do this measurement with something called like the Hubble Space Telescope, you can get images or spectra that look like this. So this is spectrum of a puffy Neptune mass planet from the Hubble Space Telescope. And you can see here that there's a big bump at about 1.4 microns. This is the indication that there's water in the atmosphere of this planet. And we were able to find that because the planet looks very slightly bigger to Hubble at those wavelengths. So you can probably tell that based on how noisy these spectra look like to the beautiful spectra that I've showed you of stars like the sun, that this field is still very much in its infancy. We're just now starting to learn about how we can study exoplanet atmospheres. How can we move forward? How can we get beautiful spectra of exoplanets so that we can learn as much about them as we can learn about stars and galaxies and other objects in the sky? The fundamental challenge is that these observations require lots and lots of light. We need to find planets that are around nearby bright stars so that we can get much more light for our instruments and we can make these very precise, difficult measurements. The more light, the easier it is to actually see something useful. The problem is that Kepler mostly discovered planets around faint stars. So this star right here in the center of this field of view is Kepler 11. This is one of the most famous systems discovered by Kepler. It has 6 planets orbiting around it. But as you can tell, it's not a particularly impressive star. It's not as bright as many of the other stars nearby. And therefore, it's very difficult for us to learn much about that star at all. By contrast, we really wish that we could find planets around stars that look like this, ones that are really, really bright, ones that we can get lots and lots of light so that we can make the sensitive measurements that we want to in order to study the atmospheres of any orbiting planets. So the reason Kepler only found planets around faint stars is because it only looked at a small patch of sky. Kepler chose one small portion of sky, about the size of this red square here, and it looked at that for about 4 years at a time. But bright stars are all around us. They're scattered all throughout the sky. If you want to find planets around all of these bright stars, these ones you can see here that I'm just kind of dotting to with my cursor, you need to look at all of the sky and look for planets around all of those stars instead of just the ones in this small region where there just aren't that many bright stars to begin with. So that is why we have built the Transiting Exoplanet Survey Satellite. This is NASA's successor mission to Kepler. Unlike Kepler, which only observed a small part of the sky, the Transiting Exoplanet Survey Satellite, or TESS, is observing almost all of the sky and looking for planets around all of the bright stars nearby. It works in almost the same way as Kepler. It takes images over and over and over and measures the brightnesses of stars. But instead of just looking at one small part of the sky, over the course of a 2-year mission, it looked at almost the entire sky. And because of that, it was able to find planets around much brighter stars than Kepler could. TESS launched in April 2018 on a SpaceX Falcon 9 rocket. Unfortunately, my video of the launch is not working at the moment, but I'll put a link to the video if you would like in the lecture notes. And I was actually fortunate enough to be at this launch. So here's a picture of me, and here's a picture of the rocket that was holding TESS a few hours before it actually flew off into space and launched the mission. It was pretty cool. I highly recommend going to a rocket launch if you have the opportunity to do so. So once TESS launched, it sent back images that look like this. You can see that it has 4 cameras, 1, 2, 3, and 4. And all of these cameras take these beautiful images of the sky. This is something called the Large Magellanic Cloud, which is one of the closest galaxies to us in the sky that's not part of our own Milky Way galaxy. This is the Small Magellanic Cloud here. And you can see that TESS just observes tons and tons and tons of stars. You can barely see all of the stars in these images here. And in the very first set of data that came down, TESS observed one star in particular that ended up being particularly interesting. This star is called Pi Mensa, and it's this one over here in the corner right here. So out of all of these stars, we single this one out. Why? The reason is that this star was already known to have a planet that was discovered back in 2002. This planet was discovered using the radial velocity method, looking for the small tugging back and forth of planets, of the star caused by a planet. It has a very distant planet, more massive than Jupiter, orbiting it every couple of years. But when TESS looked at this star, it found a second planet that was much smaller, called Pi Mensa C. And this is what the data from TESS look like. This is the brightness on the y-axis and the time on the x-axis. And you can see this dip that happened over and over again, which we've averaged all of those dips together to show you here. Pi Mensa C is exactly the type of planet that we hoped that we would be able to discover with TESS. We had studied the star for decades. We never knew about this second close-in small planet, but thanks to TESS, now we do, and we can study it and learn all about its atmosphere. And there are observations that are being done with the Hubble Space Telescope to try to learn more and more about this very interesting planet. And this is not the only success story from TESS. TESS recently released its first catalog of planets over all of the sky and has found over 2,000 possible planets. Many of these orbit stars that are very bright and nearby to Earth. So on the y-axis here, I'm showing the brightness of the stars observed by TESS. TESS discoveries are these purple, are these orange solid and orange open circles. And other surveys, previous discoveries from Kepler, are these gray ones. So you can see that the planets discovered by TESS, the ones that are orange, are typically much brighter than the ones that are discovered by Kepler. Down here are the faint stars, up here are the bright stars discovered by TESS. So TESS is really living up to its mission of finding planets around nearby bright stars. So now that we have these stars with planets that are very close to us and can give us lots and lots of light, how can we study them to find their atmospheres? The next important step that's going to happen is we're going to launch a new telescope that will let us actually study the atmospheres of these planets. Right now, the best telescope for doing this is the Hubble Space Telescope. But in perhaps later this year, in October, the James Webb Space Telescope is expected to launch. James Webb is going to be a much larger telescope than Hubble. Here's the size of the mirrors of these telescopes for comparison. The larger the mirror, the more light that mirror can collect, and the more precise we can make measurements of these planets. So we expect that James Webb will really, really help us learn lots about what the atmospheres of these planets are made of. And as an example of what we may be able to learn with James Webb compared to what we know now, this is some data of a planet called WASP 79b that was taken with the Hubble Space Telescope. We can see that there appears to be some evidence for water absorption in the spectrum. So there's a little bump here that you can kind of see in the data, which corresponds to where we think there's water causing the atmosphere of the planet to appear to look bigger to our telescopes. If we observe the same planet with the James Webb Space Telescope, our data will look like this, and we'll just get so much more information. We'll be able to learn so much more about what the atmosphere of this planet is made of, how it's structured, and all sorts of stuff. The increase in knowledge that we'll be able to get from James Webb will just be tremendous. So I'm really looking forward to when that telescope launches later this year.